Assalamualaikum. Today we will present about final year project entitled Study of the Hydrogen Storage Properties and Catalytics Mechanism of Sodium Aluminium Hydride Composites using Taguchi method. This project was assessed by our supervisor, Puan ZARINA binti OMAR. Our team member consists of Maimunatun Nawar binti YAZAN, IFFAT ASYMAWIE bin ZAHARI, binti RAZAK, and NURUL IZZAH binti AHMAD SHAKRI. Now, we will proceed to the introduction for this project. Hydrogen is the ideal energy carrier to be considered for potential transport such as automotive application. Hydrogen has attracted a great deal of attention among researchers as an ideal energy carrier used as a medium for transporting and storing energy. The storage of hydrogen in a solid state form has been one of the alternative methods due to its high gravimetric capacity and favorable safety consideration compared to the storage of compressed gas and liquid hydrogen. A variety of studies have been conducted to improve the hydrogen storage efficiency of sodium aluminum hydride, such as doping with different types of catalysts and destabilizing with other hydrides. In this research, optimal properties were identified from Taguchi method. Taguchi method used to analyze optimal condition of materials and catalysts to know which material and catalysts are suitable to get the optimal condition of onset decomposition temperature, activation energy, and hydrogen release, and whether they are significant or insignificant. The objective of our study is first to perform analysis of variance or ANOVA for signal to noise in bracket SN ratio on decomposition temperature, hydrogen release and activation energy. Second, smaller the better SN ratio and optimal condition analysis for decomposition temperature. Third, larger the better SN ratio and optimal condition analysis for hydrogen release. Fourth, smaller the better SN ratio and optimal condition analysis for activation energy. The method we use in our study is, for the first one, we extract the data from 100 journals. Then, we summarize all the data in one Excel. Third, we select the most relevant factor as our parameter and respond. Then, we key in the input data into Minitab software. Next, we analyze the data using Taguchi method, and the last one, we determine the optimal factors and level.
For the first performance, which is analysis of variance or ANOVA for signal to noise in bracket SN, ratio on decomposition temperature, hydrogen release and activation energy. Decomposition temperature is the temperature at which the substance chemically decomposes. The hydrogen release is the amount of hydrogen released during the process happens. For the activation energy is the minimum amount of energy that is required to activate atoms or molecules to a condition in which they can undergo chemical transformation or physical transport. In ANOVA table, we have 6 columns consist of the first one, degree of freedom or DOF. DOF are the amount of information in the data. The analysis used the information to estimate the value of unknown population parameter. The second column is sum or square. It's a measure of the deviation of the experimental data from the mean value of the data. Taguchi used the adjusted sum or square to calculate the p-value for a term. The third one is mean square. Also called variance, measure the distribution of the data about the mean of the data. Mean square measure show how much variation a term or a model explain, assuming that all other terms are in the model regardless of the order they were entered. In ANOVA table, we have F value represented the statistical calculation by the effect of the control factor to the response. When the F value higher than 4, it represents that the control factor have the powerful impact on the response. For the P value, it reports the significant level or otherwise for the control factor. When the factor with the P value lower than 0.05, it provides the strongest significance to the response. The last column is significance column. When the p-value higher than 0.05, it indicates that it is insignificant to the response and otherwise. From the result ANOVA analysis on decomposition temperature, it shows that the catalyst is significantly contributing towards the sodium aluminum hydride performance. This is because the p-value, which is 0.011, is lower than 0.05. Besides, as we can see in the table 1, the
Catalyst rule shows that at the column of F value, the number is bigger than 4. It means that the catalyst have a strong impact to the performance.
For the ANOVA analysis on hydrogen release, it showed that the material and catalyst is insignificant towards the performance. This is because the p-value higher than 0.05. Last but not least, the ANOVA analysis on activation energy showed that the catalyst is significant to affect the performance of sodium aluminum hydride. As we can see here, the p-value is 0.032 below than 0.05.
So let's move to the next slide. That is smaller the better, SN ratio and optimum condition analysis for decomposition temperature. From here, there are two tables that are result of confirmation test and optimum condition for decomposition temperature, and also response table for SN ratio. To have the higher rate of chemical reaction, decomposition temperature need to be low. So the lower decomposition temperature is the optimum condition for catalyst and material. So from the table, from the response table for SN ratio, the level sits from catalyst is the lowest value. That means the optimum condition of the catalyst is at level 6, there is non-catalyst. And from material, the lowest value is at level 3. That means optimum condition of the material at level 3, that is NaAlH4, LiBH4. So let's proceed with the smaller the better SN ratio plots for decomposition temperature. From the graph, shows that mean of SN ratios for different catalysts and material. Smaller is better makes non-catalyst and NaLH4, LiBH4 material is optimum level for decomposition temperature with the low value.
So now I will talk about the larger the better SN ratio and optimal condition analysis for hydrogen release. So as you guys can see, the blue table is the result of confirmation test of optimal condition, while the red table is the response table for SN ratio. So in this study, the larger the better type of analysis was selected since the highest hydrogen release is always desirable. The largest SN ratio corresponds to the optimal characteristic. In table blue, which is result of confirmation test of optimal condition, summarize the control factor and their level of SN ratio. As can be seen, the optimal condition are the catalyst of level 2, which is NBF5, and system of level 3, which is NaAlH4, LiBH4. So system means here is the material. So among these control factors, catalyst is the most influential factor affecting the response. This is due to the largest difference in the delta response table for SN ratio. It is because change in catalyst will affect the result on hydrogen release capacity. So this is the graph for the larger is better plot for hydrogen release. So the graph shows that the line is up and down due to the increasing of catalyst on the effect of NBF5 from table response for SN ratio, which contribute to the higher SN ratio and higher material. So that's all from me. Thank you.
I will proceed to the smaller the better SN ratio and optimal condition analysis for activation energy. In this study, the smaller the better type of analysis was selected since the smallest activation energy is always desirable. This is because the activation energy of a particular reaction determines the rate at which it will proceed. The higher the activation energy means the slower the chemical reaction will be. In order for reaction to occur at significant rate, activation energy must be lowered. The smallest SN ratio corresponds to the optimal characteristic. This table shows the result of confirmation test at optimal condition. This is the response table for SN ratio on activation energy. As we can see from the table SN ratio, The optimal condition of catalyst is at level 6, which is none, and optimal condition for material is at level 2, which is sodium aluminum hydride with magnesium hydride. This is because they have the smallest value of SN ratio. And we can see that among these factors, catalyst is the most influential factor affecting the response due to the largest difference in delta. This is the smaller, the better plot for activation energy. Based on this graph, as the catalyst changes to none, which means no catalyst is used, it contributes to the lowest SN ratio and smaller activation energy.
In conclusion, based from our study in our final year project, the first thing we get is the optimization for multi-response process parameter of decomposition temperature, hydrogen release and activation energy were done using Taguchi orthogonal method, which offer a systematic and efficient way to select design parameters. Second, the analysis is done by applying smaller the better criterion for decomposition temperature, larger the better for hydrogen release, and smaller the better criterion for activation energy. In the present study, analysis of Erice or ANOVA indicate that the material is insignificant for all parameters, while catalyst being significant for decomposition temperature and activation energy. The fourth one is the optimal condition of control factors for decomposition temperature are 340 degrees Celsius, hydrogen release 8% and activation energy 128 kJ per mole. The result of the signal-to-noise or SN ratio analysis revealed that catalyst has the greatest impact among the control parameter study. Ultimately, we would like to express our special thanks of gratitude to ZARINA for the guidance and support in completing the report. That's all from us and thank you.